Hey there guys, in this one we are walking through AQA's AS level further maths specimen paper 1, which I'm sure is going to be a whole heap of fun. Let's go. Okay, question 1. So a reflection is represented by the matrix 1, 0, 0, minus 1. We want to state the equation of the line of invariant points. So invariant points are points that don't move when the transformation, so here the reflection, takes place. So if you struggle to remember what these matrices do, like me, because I don't do further maths very often, what we can do is pick 2 points on the axes. So I'm going to pick this point here, 1, 0, and this point up here, 0, 1. And then what we're going to do is multiply the position vectors of each of these points by the matrix and see where they end up. So first of all, if we do 0, 1 times, we're not going to do that at all, we're going to do 1, 0, 0, minus 1. First of all, let's multiply that by 1, 0. So that would give us up on top 1 times 1 add 0 times 0. So that's going to give us 1. And then on the bottom, 1 times 0 add minus 1 times 0, which is still going to give us 0. So it turns out that point 1, 0 is invariant. So let's then do that for the other point, 0, 1. So this time 1, 0, 0 minus 1 times 0, 1. So up on top we're going to get 0 times 1 add 1 times 0. So up on top we're still getting 0. On the bottom we're going to get 0 times 0 add 1 times minus 1. So we're going to get minus 1 on the bottom. So what's happened is the point 1 has been reflected down here to 0, minus 1. Now, that other point 1, 0 is invariant. So what we've done, we've reflected in the x-axis. Now the equation of the x-axis is y equals 0. Good times. Okay, question 2. We want to find the mean value of 3x squared over the interval x is greater than or equal to 1 and less than or equal to 3. So, the mean value of a function is 1 over the size of the integral. So we're going to say that's 1 over b minus a of the integral of the function with respect to x between the limits of the interval. So here we're going to have 1 over 3 minus 1, which is 2, times the integral between 1 and 3 of 3x squared. Okay, so if we integrate 3x squared with respect to x, we get x cubed. So this is equal to 1/2 of x cubed between 3 and 1, which is 1/2 of 3 cubed is 27. So we get 27 minus 1 cubed, which is 1. So we got 1/2 of 26. So the answer is 13. There he is. Cool. Question 3, we want to find the equations of the asymptotes of the curve x squared minus 3y squared is equal to 1. So asymptotes like to occur when the bottom of a fraction is equal to 0. At the moment we don't have any fractions, but what we're going to do is divide both sides of this by x squared minus 3y squared. So this can become 1 is equal to 1 over x squared minus 3y squared. So problems are going to occur when x squared minus 3y squared is equal to 0. So notice here all of our options are in terms of y equals something to do with x. So we're going to set x squared minus 3y squared equal to 0 and solve that for y. So if we add 3y squared to both sides, x squared is 3y squared divided by 3, x squared over 3 is equal to y squared, and then finally square root. So y is going to be plus or minus x over root 3. So it's this chap at the end. Good times. Okay, question 4, we got some matrices fun. So part A says find the value of k for which matrix A is singular. So if A is singular, and then the determinant will equal 0. Okay, so from that, the determinant then is 1 times k minus 2 times 1. Now we know that is equal to 0, so that gives us k minus 2 is equal to 0, therefore k is equal to 2. Cool. Part B wants us to describe the transformation represented by matrix B. So again, to do this, I'm going to pick those same 2 points. One, 0, and 0, 1, and see what happens to them when we multiply them by the matrix. So, -1, 0, 0, 1, multiplied by 1, 0. Well, that's going to give us, up on top, 1 times -1, add 0 times 0. So that's going to give us -1. And then on the bottom, we get 1 times 0, add 0 times 1. So that is going to be 0 on the bottom. So this point at 1, 0 has moved over here to -1, 0. Okay, now let's see what happens to 0 or 1. So again, -1, 0, 0, 1 times 0, 1. Up on top, we are going to get 0 times -1, add 1 times 0. So we're still going to get 0 up on top. And on the bottom we get 0 times 0, add 1 times 1, which just leaves us with, again, 1 on the bottom. So this time, the point on the y-axis is invariant. So what we've done, we've reflected in the y-axis. So it's a reflection in the y-axis. Then part CI wants us to, given that matrix A and B are both non-singular, we want to verify that A inverse times B inverse is the same as BA inverse. So, quite a lot to do here. This is the formula to find the inverse of a 2x2 matrix. So if M is equal to ABCD, then M inverse is 1 over the determinant of the matrix times D minus B minus C A. So what happens along the left to right diagonal, the two numbers swap places, and then along the diagonal from bottom left to top right, both of those numbers become the negative of what they were. So, first of all, I'm going to go for finding BA inverse. So to do that, I'm going to first of all need to find BA. So BA is going to be -1, 0, 0, 1 multiplied by 1 to 1k. Okay, so that's going to give us, in the top left, we are going to have 1 times 1, no, sorry, 1 times minus 1, add 1 times 0. And then top right, we're going to have 2 times minus 1, add 0 times k, bottom left, we're going to get 1 times 0, add 1 times 1, and then bottom right, we're going to get 2 times 0, add 1 times k. So, if we sharpen that up, we get BA is equal to minus 1 and then minus 2 and bottom left is 1 and then bottom right is just k. Cool. So that is our matrix BA. What we then want to do is find the determinant of this chap. So the determinant of BA is going to be minus 1 times k minus 2 times 1. So that is minus k add 2 or 2 minus k. So now we can find BA inverse. So BA inverse is 1 over the determinant, so 1 over 2 minus k times k. So the minus 1 and the k swap places, so we get k there and minus 1 there. The minus 2 in the top right becomes positive 2, and then the positive 1 bottom left becomes minus 1. So there we have our expression for BA inverse. So now what we're going to need to do is find A inverse and B inverse and see what we get when we multiply them together and hope it's the same as this. Okay, so for matrix A then, the determinant is 1 times k minus 2 times 1, so that's k minus 2. So A inverse is 1 over k minus 2 times, well, the 1 and the k swap places diagonally, so we get k top left, 1 bottom right, and then the 2 and the 1 in the bottom left and top right become negative. So we get -1 down there and -2 up in the top right. So that is A inverse for B. Well, the determinant is -1 times 1 minus 0 times 0. So that is -1. So B inverse is 1 over -1 times, well, the 1 and the -1 swap places, and then nothing really happens with the zeros. So that is our B inverse. So A inverse B inverse is 1 over k minus 2 times 1 over -1. Lots of k minus 2 minus 1, 1 times 1, 0, 0 minus 1. Okay, so this fraction at the start, if we combine it into 1, is 1 over minus k plus 2. So we got this, we're multiplying by -1 on the bottom. So this guy at the start does become 1 over 2 minus k. So that's a good start because we had that for the first part of this question in BA inverse. So that's a good sign. Okay, so then if we multiply these two matrices, top left, we are going to have 1 times k add 0 times -2. So that's going to give us k in the top left. Top right, we're going to have 0 times k add -1 times -2. So that's just going to give us positive 2 in the top right. Bottom left, we're going to have 1 times -1 add 0 times 1. So that's just going to give us -1. And then bottom right, we're going to have 0 times -1 and add -1 times 1, which is going to give us -1. Now that is exactly the same as what we worked out back here for BA inverse. Therefore, we can say then A inverse B inverse does indeed equal BA inverse. Good times. Okay, final part of question 4. We want to prove the result that M inverse N inverse is always equal to NM inverse for all square matrices M and N that are non-singular. So my first moan here, why do we always have to use two letters that look the same and sound the same? So again, this is the result that we are trying to prove. M inverse N inverse is equal to N M inverse. So one thing that we're going to need to remember here is that a matrix times its inverse is exactly the same as the inverse times the original matrix, which is equal to the identity matrix. So what we need to spot here is that we could multiply both sides by N M inverse. So using this result above, we know then that N M times N M inverse is equal to the identity matrix. So what we can say here then is that if this statement is true, so if M inverse N inverse is equal to N M inverse, then that means if we multiply both sides by N M, then N M times M inverse N inverse has to equal the identity matrix. So that is now what we're going to try and prove. Now, this is one long chain of matrix multiplication. So we can say then that N M times M inverse N inverse, well, we can say that that is equal to N times M inverse times N inverse. Now in the middle here, we've got N times M inverse times N inverse at the end. Now the bit inside the bracket, M times M inverse, we know is the identity. So this is equal to N times the identity times N inverse, which is just N times N inverse, which is indeed equal to the identity. So we've proven that it's true. Therefore, the conjecture is true for all non-singular M and n square matrices of the same size. We've done it. Question 5. So the area bounded by the curve with equation y equals 3 plus root x, the x-axis and the lines x equals 1 and x equals 4 is rotated 2 pi radians about the x-axis. We want to show that the volume generated is 125 pi over 2. So, volume of revolution. The formula is V is equal to pi times the integral of y squared with respect to x. So, first of all we need to find y squared. So y squared is 3 plus root x squared, which is 9 plus 6 root x plus x. So our volume is pi times the integral between 1 and 4 of 9 plus 6x to the power of a half plus x with respect to x. So this is pi times, well, our integral is 9x, 6x to the power of a half, well, x to the power of a half integrates to x to the 3 halves. So we then divide that term by 3 halves. So 6 divided by 3 halves is 4. So we got 9x plus 4x to the 3 halves, add x squared over 2 between 4 and 1. So this is pi lots of. So 9 times 4 is 36. Then we got 4 lots of 4 to the power 3 halves. 4 to the 3 halves is 4 cubed square rooted. 4 cubed is 64. 64 square rooted is 8. So we got plus 4 times 8, which is 32. And then add 4 squared over 2, which is 16 over 2, which is 8. And then we are minusing. So minus 9 times 1 is 9. And then 4 lots of 1 to the 3 halves is just 4. And then x squared over 2 is just going to give us a half. So we have got pi lots of 36 and 32 is 68 and 8 is 76. So we got 76 minus, 9 add 4 is 13, so we got minus 13, and then minus 1/2. 76 minus 13 is 63. So we got 63 minus 1/2. So that is pi times 62 and a half, which does indeed equal 125 halves times pi. Good times. K6A wants us to use the definitions of sinh and cosh of x in terms of e to the x and e to the minus x to show that x is equal to 1/2 log 1 plus t over 1 minus t, where t is tanh x. So, first of all, the definitions. Sinh of x is e to the x minus e to the minus x all over 2, and cosh of x is e to the x add e to the minus x all over 2. And we're also going to need to know that tanh of x is sinh over cosh. So tanh is sinh x over cosh of x. So, in the exponential form then, we can say that tanh of x is e to the x minus e to the minus x all over 2 divided by cosh of x. So, divided by e to the x plus e to the minus x all over 2. So that gives us tanh of x is e to the x minus e to the minus x all over e to the x plus e to the minus x. Okay, so from here on out I'm going to call tanh t. So we don't like that we have two different types of exponential term on the top and bottom of this fraction. So what we're going to do here is multiply top and bottom by e to the x. So what that's going to do is sort out the e to the minus x terms. So e to the x times e to the minus x is just 1. E to the x times e to the x is e to the 2x. So here then we can say t is e to the 2x minus 1 over e to the 2x plus 1. Now, we want to get x on its own, so the fact that we have an e to the 2x down here on the bottom of the fraction is problematic. So the next step is to multiply both sides by the bottom of the fraction. So we get t, I'm going to expand it as well, t e to the 2x plus t is equal to e to the 2x minus 1. We now want to get the e to the 2x terms on the same side with anything else on the other. So I'm going to add 1 to both sides and subtract t e to the 2x from both sides. So I'm going to get 1 plus t is equal to e to the 2x minus t e to the 2x. Now, on the right, we have a common factor of e to the 2x. So I'm going to factorize. So I'm going to say we got 1 plus t is equal to e to the 2x times 1 minus t. So, from there, if I divide both sides by 1 minus t, I've got 1 plus t over 1 minus t is equal to e to the 2x. Now we need to get that 2x out of the exponential, so we're going to take the natural log of both sides. So we then got log of 1 plus t over 1 minus t is equal to 2x. And then for our final step, we need to divide by 2. So now we can say therefore x is indeed 1/2 log of 1 plus t over 1 minus t. Good times. Okay, then part B wants us to prove that cosh cubed of x is equal to 1/4 cosh of 3x add 3/4 cosh of x. So, we're going to need to use the exponential form. So, in exponential forms, then we want to prove that e to the x add e to the minus x over 2 all cubed. We want to prove that that is equal to, well, 1/4 cosh of 3x is e to the 3x, add e to the minus 3x all over 2, and then we got add 3 quarters cosh of x, which is e to the x, add e to the minus x all over 2. So, how are we going to do this? Well, there's the thing that we want to prove. What we're going to do is deal with this bracket here, so the cosh cubed bracket. We're going to expand all of this and make sure that we can write it as the stuff on the right. So, e to the x, add e to the minus x over 2 all cubed. First of all, we can think of that as 1 over 8 times e to the x, add e to the minus x cubed. So all we've done there is cube the 2 on the bottom and then put it out on front. So we need to expand e to the x, add e to the minus x, all cubed. So we're going to do this bit by bit. So e to the x, add e to the minus x. If we just square it, first of all, so we're going to multiply it by itself. Well, for that, we're going to get e to the x times e to the x is e to the 2x. Then e to the x times e to the minus x is just 1. So we're going to get that twice. So there's going to be a plus 2. And then there's going to be an e to the minus x times e to the minus x term, which is e to the minus 2x. So at the moment, that's e to the x add e to the minus x squared. So we now want to multiply that by e to the x add e to the minus x. So if we do e to the x add e to the minus x times e to the 2x add e to the minus 2x, well, we're going to get e to the x times e to the 2x is e to the 3x. E to the x times 2 is going to give us plus 2 e to the x, and then e to the x times e to the minus 2x is going to give us e to the minus x. And then we're doing e to the minus x times e to the 2x. So that's going to give us a plus e to the x. And then e to the minus x times 2 gives us plus 2e to the minus x. And then e to the minus x times e to the minus 2x gives us plus e to the minus 3x. So that's what we get for e to the x add e to the minus x cubed. So at the moment then we can say cosh cubed is 1/8 of all of that stuff written above. So let's see if we can simplify this and make it look a little bit nicer, or at least collect like terms. So we've got an e to the 3x, which is the only term like that. So we got e to the 3x. Now we've also got a plus e to the minus 3x. So let's put those together like that. Now let's cross these out as we go. So e to the 3x and e to the minus 3x have gone. Okay, then our next term is 2e to the x, and we've also got a plus 1e to the x. So altogether we got plus 3e to the x. So let's cross those out. That's this going on and this going on. And then we've also got a plus e to the minus x plus 2e to the minus x. So that is plus 3e to the minus x. Okay, so that looks a little bit nicer, maybe. So if we notice something here, the first two terms inside the brackets are e to the 3x and e to the minus 3x. Now they will go quite nicely together into a cosh term, as will 3e to the x add 3e to the minus x. So what do I mean by that? Well, we could write this as 1/8. So e to the 3x add e to the minus 3x add 1/8 of 3e to the x add 3e to the minus x. Now, these two things now that are inside the brackets are almost looking like expressions for cosh. So, what we can do now, the only thing that e to the 3x add e to the minus 3x is missing is that factor of 2 on the bottom. So what we can do, we can say this first guy is 1/4 e to the 3x, add e to the minus 3x over 2. So that is 1/4 cosh of 3x. So that's cool. And then this second guy, first of all, both terms inside the brackets have a factor of 3. So we're going to bring that 3 out. And just like we did with our last bracket, we're going to take a factor of a half inside the brackets. So we're going to say this is 3/4 e to the x, add e to the minus x, all over 2, which is the same as 3/4 cosh of x. So we've proven what we wanted to prove. We can put a cheeky little QED because we definitely feel clever. Good times. Okay, then the final part wants us to show that the equation cosh of 3x equals 13 cosh of x has only one positive solution. We want to give this solution an exact logarithmic form. So, bit of a problem, we got cosh of 3x and a cosh of 1x. So we got two different types of cosh term. Luckily though, the equation that we used here is going to help us in this question. So, from this equation, cosh cubed of x is equal to 1/4 cosh 3x, add 3/4 cosh of x. So we can rearrange this to make cosh 3x a subject. So if we first of all multiply through by 4, we get 4 cosh cubed of x is equal to cosh 3x add 3 cosh of x. So, therefore, cosh 3x is equal to 4 cosh cubed of x minus 3 cosh x. So now we can substitute this into the equation that we're trying to solve. So this equation is cosh of 3x is equal to 13 cosh of x. So we now know what cosh of 3x is in terms of cosh of a single x. So, substituting that in, we get 4 cosh cubed of x minus 3 cosh of x is equal to 13 cosh of x. Now, if we take away the 13 cosh of x, we end up with 4 cosh cubed of x minus 16 cosh of x, and that is equal to 0. Okay, so we got a common factor here of cosh of x. Actually, before we do that, we've got a common factor here of 4, which we can divide away. So we get cosh cubed of x minus 4 cosh of x is equal to 0. And now we have a common factor of cosh of x, so we can factorize this to cosh of x times cosh squared of x minus 4 is equal to 0. Okay, so up to here, this would suggest then that cosh of x can equal 0 or 2 or minus 2. So 2 and minus 2 come from cosh squared of x minus 4 equaling 0. So if you add 4 in square root, cosh of x is plus or minus 2. However, 2 of those solutions are rubbish, and that is 0 and minus 2. The range of cosh of x is greater than or equal to 1. So those possible solutions of cosh of x equals 0 and minus 2 can't happen because they are both less than 1. So the only solution then is cosh of x is equal to 2. So we want to find the value of x for this solution, or this is the solution, the value of x. So now we're going to convert to exponential form. So cosh of x again is e to the x add e to the minus x over 2, so that is equal to 2. If we multiply by 2, e to the x add e to the minus x is equal to 4. Okay, so we now need to solve this equation for x. So your graphical calculators can do this from the cosh of x equals 2 part, but I can't find mine, and where's the fun in using a calculator? So, to solve this, we're first of all going to multiply through by e to the x. So we're going to get e to the 2x, add 1 is equal to 4e to the x. Now if we take away the 4e to the x, we can get e to the 2x minus 4e to the x plus 1 is equal to 0. Now this guy is a quadratic equation. If we say that e to the x is equal to y, then e to the 2x is equal to y squared. So we could rewrite this as y squared minus 4y plus 1 is equal to 0. Now, to solve this guy, well, we could complete the square. So let's do that. So if we complete the square, this will be y minus 2 squared, and then plus 1, then minus 4 on the outside. So that's going to give us minus 3 equals 0. Add the 3, y minus 2 squared is equal to 3 square root y minus 2 is plus or minus root 3. And then add 2, we get y is 2 plus or minus root 3. Okay, now remember, y is e to the power x. So e to the power x can be 2 plus or minus root 3. Now, we need to log both sides. So we would get x is either log of 2 minus root 3 or log of 2 plus root 3. Now, what you will find is that log of 2 minus root 3 is negative. We are interested in positive solutions, so the only positive solution is log of 2 plus root 3. Far more work probably than was necessary there, but it's nice to go through these things and do them without a calculator.